When you are deciding who to marry, you are using an algorithm. The same is true when you are looking for a parking space, playing a game of poker, or deciding whether or not to organize your closet. Algorithms to Live By is a book about the computer science of human decisions. It offers strategies for how to think through everyday life like a computer scientist. Brian Christian has a background in computer science and philosophy and is an author of Algorithms to Live By. He joins the show to explain how the same algorithms and data structures that we use for our computer programs can be applied to the real world. I really enjoyed this episode. I enjoyed Brian's book, Algorithms to Live By, and I think you will enjoy them as well. So, you've got a bacon delivery service, and you need to notify your customers when their bacon has arrived at their doorstep. Twilio helps you make sure your customers get the bacon while it's hot. Twilio's programmable API lets you build SMS or voice alerts easily in the programming language of your choice, all in under 5 minutes with only a few lines of code. Now your customers get a text or a call the instant their bacon is ready. If your customers want to see the bacon frying on a hot pan, Twilio has video APIs and SDKs for the platforms that you know and love. Learn more at go.twilio.com/podcast and get an additional $10 when you sign up and upgrade your account. That's go.twilio.com/podcast. You will only pay for what you use, and it costs less than a penny to send a text. Get started at go.twilio.com/podcast. Get your bacon delivery service cooking with Twilio's APIs for voice, SMS, and video. Brian Christian is a co-author of Algorithms to Live By. Brian, welcome to Software Engineering Daily.
Thanks so much for having me. Algorithms
to Live By is about the computer science of human decisions. What does that mean?
The basic premise of the book is pretty straightforward to articulate. You know, there's a class of problems that all of us face in everyday life, whether it's, you know, choosing the apartment we want to live in, or deciding where to go out for dinner, or managing our messy offices, or scheduling our time. And we think of these as, in some sense, intrinsically and uniquely human problems. And the message of the book is, in fact, they're not. They correspond rather profoundly to a set of some of the fundamental problems in computer science. And so this gives us a real opportunity to learn something about how to make better decisions in our own lives by thinking about the structural properties of the problems that we face and what the ideal optimal solutions for those problems look like.
And many of the algorithms that you discuss in the book are things that were designed for computer systems. How closely does our everyday life resemble a computer system?
Yeah, I mean, I think there are a surprising number of ways in which these formal problems kind of rear their head in everyday life. And so one of the examples that we make in the book is, you know, if you imagine that you are looking to, you know, rent an apartment, say, or buy a house. Let's just go with the example of renting. So you go to you see a listing on Craigslist, you show up, and you like the place pretty well, and you have to decide, you know, do you take this apartment, or do you walk away and consider your options for another week and explore other open houses? But, excuse me, but in doing so, you lose the opportunity to go back. And so here you're in this type of a problem that's known as an optimal stopping problem. So you have to make a decision at each step along the way. Do I take the option in front of me, in which case I kind of forsake all possible future options that could be better? I'll never know what else might have been out there. Or do I walk away to keep exploring what's out there, but in so doing, I may lose the opportunity in front of me? And so I think this is kind of a classic human dilemma. It plays out not only in apartment hunting, but, you know, if we're driving down the street and we see a parking space, we have to ask ourselves this question of, do I take the space right here, or do I keep going and take the gamble that there might be a better space ahead? And, many people have argued that this is also kind of a rough description of dating, right? So we're in a relationship, and at some point you have to make a decision about, do you commit to this person and not know who else might have been out there? Or do you break up in order to meet other people, but you may forfeit the ability to change your mind and go back if you feel you've made a mistake. And
you call this explore versus exploit in the book.
This specifically is an area called optimal stopping.
Oh, this is optimal stopping, right?
Mm-hmm, mm-hmm.
Okay.
So, problems that have this structure of you're presented with a sequence of opportunities, and at each step in the sequence, you either stop on the option in front of you or you continue on. And so, here's a case where by identifying the underlying cognitive or computational structure to the problem, it gives us a way of making sense of it and a way of sort of recognizing the type of situation that we're in. And the classic version of the optimal stopping problem is called the secretary problem. And it's a similar structure. You have you're hiring a secretary, and X number of candidates show up in a random order, and you interview them one at a time. At each point in time, you can either hire the person or dismiss them. And there's this wonderfully simple optimal solution, which says that if you want to get the best chance of hiring the very best candidate, don't commit to anyone for the first 37% of the candidate pool, and then immediately hire the next person who's better than everyone you saw in the first 37%. And so you can translate this principle, for instance, directly into the apartment hunt context. So if you've given yourself a month to find an apartment, and you want to give yourself the best chance of finding the very best apartment, then you should spend the first 37% of your search, so in this case 11 days if you've given yourself a month, non-committally exploring your options. And then after that initial 11 days, be prepared to immediately jump on the first thing you see that's better than what you saw in those first 11 days.
Now, that is, of course, a useful framing, but it's also a somewhat more rigid framing than life actually presents us with, because very often in this type of scenario, we allocate 11 days, and we decide that after 37% of that time, we're going to do, like you said, the next option that we get that's better than all the previous options we'll go with. But in real life, during the first portion of those 11 days, we might say, I don't want to live in this neighborhood at all. I don't want to live in this place at all. There are so many edge cases that occur in real life. So how do you contrast that rigid, algorithmic way of living life versus the richness and the complexity of the decisions of everyday life as they actually appear?
Mm-hmm. Yeah. So, one of the things that comes up in the book, in every chapter, we, having broken down the essential mathematical structure of the problem and looked at the things that characterize the optimal solutions to those problems, there is, of course, this irresistible question, which is that what people actually do when they are put in that situation? And in most cases, the answer is a resounding no. So, for example, if you put undergraduates in a psychology study into a lab environment, and you get them to do these optimal stopping type problems, do they inherently, kind of intuitively implement the 37% rule? The answer is no. They appear to do something pretty close to it, but they consistently stop earlier than they should. They appear to implement, for example, something roughly equivalent to a 31% rule. And so you can offer a number of explanations for this discrepancy. And some people have argued, well, humans are just kind of risk averse. They would rather take a suboptimal thing than, risk the chance of being empty-handed. And there's one particular interpretation of the data that I find, that I find particularly interesting, which is someone had a look at the raw data from this particular experiment, and they found that human judgment matches up really closely to the optimal strategy if you are assessing, let's say, a 1% utility penalty for each additional option considered. And they found, well, this is weird because there was no such penalty, so why were people acting as though there was? And I think a fair answer to that is, well, they're human. They're real people doing a fairly boring and repetitive psychology experiment, and they would just as soon be done with that rather than prolonging the experiment. And so, my collaborator Tom and I talked to some of the psychologists that have done these experiments, and they say, yeah, it's understandable that the subjects just get kind of bored and restless, but we don't have a way to rigorously model that. And so here's a case where, whenever there's a discrepancy between the formal prediction and actual human behavior, you have an opportunity to ask this question of who's wrong? Are the people wrong, or are the models wrong? And in many cases, we actually end up coming down on the side of human intuition and saying, it seems like what's happening is people are implementing a sensible solution to a subtler version of the problem than the one that the experimenters thought they were solving.
Certainly. Okay, so let's talk about some of the other fundamental questions that you look at in Algorithms to Live By. One is the trade-off between space and time. This is a classical computer science trade-off exchange. Computer scientists understand this trade-off. How does the trade-off between space and time manifest in our everyday world?
I think the most clear example would be something like, organization, right? Like your home office organization and so forth. Now, ideally, let's think about this. I mean, in some ways, there's an even earlier trade-off that you have to make, which is effectively between time and time. So, in a home organization context, we talk about what's called the search-sort trade-off. So this is something that comes up in computer science context related to database management, for example, and this also relates to the space-time trade-off. So, if you're a database administrator, you have this question of what indexes do you implement in your database? Do you put in an index for every possible column and every possible table? Well, that's going to consume extra space. Because you're going to have to store those indexes. It's also going to consume extra time on every insert and delete, because you're now also going to have to update the index. But as a result, the upside of that trade-off is that it becomes much easier to find things. And so the way that a computer scientist would approach a problem like this is to say, well, is it going to take us more time to create this index than we are going to save down the road by having the index? And so this is a principle that we raise in the context of, whether or not to alphabetize your bookshelf, for example. That there is this question of, is it going to take you more time to get organized than you will save by being organized? And in many domestic contexts, we argue that is in fact exactly what happens. And so I think counterintuitively to a lot of people, we think of computers as the paragons of, orderliness. But in fact, if you look at how caching schemes work, computers are much messier than they let on. And moreover, I think computer science gives us, perhaps surprisingly, the framework and the language with which to articulate the pro-mess argument. That sometimes mess is not just the easy choice, but it is, in fact, the optimal choice.
Software Engineering Daily has 20,000 engineers listening Monday through Friday. If you are hiring, or if you have a product that you would like to get into the hands of engineers, send me an email, jeff@softwareengineeringdaily.com. This podcast is sustained by the advertisers, and if you would like to become one, or even if you're just curious and you want to learn more, send me an email, jeff@softwareengineeringdaily.com. Thanks for listening.
In computer science, we're often talking about data structures along with our algorithms, and many times the data structure lets us cheat our way out of an algorithm that might have been seemingly impossible. Like I think of the hash map as the classic example of this, where it's like a hash map is just like cheating compared to all of the things that you can do without, or what you're capable of doing without a hash map. But there's not really I don't, when I think about it, maybe you can say something different, but when I think about a hash map, I don't think there's like a logical construct in the real world that maps to a hash map. So are there data structures to live by, or are is algorithms to live by what we're limited to in the real world?
Yeah, that's a great question. And I was reminded of when Tom and I were doing some of the interviews for this book. We went up to Harvard and we talked with Michael Mitzenmacher, who is an expert on hashing algorithms, and he insisted on taking the interview outside of his office because it was full of this chaotic mess of papers that he did not want to disturb in any way, lest it upset his highly precise caching system, or hashing system, I should say, in which, he just knew where every object would be found if it were there. So I think that's one of the ironies of human life, which is that, the thing that most mimics this kind of order of one hash lookup system is chaos. But as long as you remember where everything is in that chaos, then you're fine. Of course, if you forget, then you have to look through it at random, and you're now you're living in the order of n world. But to your question of how data structures work, I mean, I think if you think about something like a bookshelf, there's this open question of to what what data structure best describes a bookshelf. An alphabetized bookshelf is a little bit like a binary tree, because if you're looking for a book that's an M or an N, you know to look in the middle, and then if to look to the left or right of that, and you can kind of intuit your way towards the item, and it's not exactly clear how that maps to a data structure where you have a basic idea of where to index it. The other thing that we talk about in the context of bookshelf organization is, typically, if you want to make some optimality argument about a particular algorithm, you're minimizing the total number of operations, but there's not always a clear separation between the types of operations that you're talking about. So, for example, if I'm trying to organize my bookshelf, I'm trading off the amount of time it will take me to kind of insertion sort these books into place versus the amount of effort it will take me to scan the spines for something I'm looking for later. But there's a fundamental disconnect, which is that I'm sorting with my hands, which are orders of magnitude slower than my eyes, and I'm searching with my eyes. So there's a little bit of an apples to oranges thing that's happening there. Another one of the interviews that Tom and I did was David Karger at MIT, who talks about data structures, and we had a long conversation about exactly to what degree do human physical object schemes map to some of the canonical data structures in computer science, and it's kind of an interesting open question.
Yeah, so one of the algorithms that I think of as just a brilliant merger of algorithms and data structures is Dijkstra's algorithm, which is uses priority queues in a very creative way, and obviously it's an efficient way of finding the shortest path between a source node, and all destination nodes. And Dijkstra's algorithm seemed like this. Just like, how would you come up with Dijkstra's algorithm? So when you were doing research for this book, and you're looking at the different computer scientists who solved these really hard problems, you talk about Dijkstra some in the book, but was there something unique about Dijkstra? He was very literary. He wrote a lot, I know. Maybe you could give some information about Dijkstra and how he compares to other computer scientists, and what your thoughts on Dijkstra's algorithm are.
Yeah, I mean, Dijkstra's algorithm is very near and dear to my heart, because one of my early computer science projects when I was an undergrad was I looked at this data structure for language called WordNet, which someone took the trouble to kind of semantically categorize all the words in English, into this tree structure of, a collie is a dog, is a mammal, is an animal, is a physical thing, something like that. And so it occurred to me that you could use Dijkstra's algorithm to traverse WordNet and find some numerical representation of the similarity between pairs of words, right? So how many hops is dog from frisbee or something like this? And this put the idea in my head that you could characterize human speech by looking at, the distribution of, the WordNet distance between neighboring words. And so I ended up doing a research project where I took the Shakespeare, some control group of normal, just regular human beings, versus Shakespeare versus the speech of schizophrenics. And within each corpus, I calculated, various metrics using Dijkstra's algorithm to connect the different adjacent pairs of words in WordNet. And it was able to find statistically significant differences between all three sets of data. So I remember vividly that my computer spent, the better part of the summer just grinding away, computing Dijkstra's shortest path on, tens of thousands of words. I mean, I think, there's no doubt that Dijkstra is one of the brilliant minds of, even among, some of the canonical computer scientists.
I mean, I did an interview with Leslie Lamport a couple years ago, and he referred to Dijkstra as being really a formative influence in his own work. And when I think about other people who have come up with very creative algorithms that are solutions to, like, just these brilliant solutions that are super creative to really, really hard, important problems, Leslie Lamport certainly falls into that category as well. And yeah, regarding what you said about Dijkstra, like that algorithm, there was a show I did recently about Netflix's movie recommendation algorithms, how it looks these days, and they build things that look like maps of locations, but it's movies, and they run Dijkstras on movies to find the nearest neighbors, or the things that would be not geographically, but
geographically in some weird space. Yeah.
Right, exactly. So it's not just like this traveling salesman in the sense of a physical physical location type of algorithm solution. It's applicable to this very rich set of problems. So I want to shift to something.
And I just want to
go ahead.
I just want to add on to that. I mean, the other thing that comes to my mind when I think about Dijkstra is the famous "go-to considered harmful." that he was one of the people thinking about the structure of programming itself. And this makes me think of we had actually wanted to include a chapter in the book. It ended up not making it into the final printing, but we had a section that looked at data structures and depth first search versus breadth first search, and the ways in which you could consider the execution of a program itself as being kind of a traversal, basically a depth first traversal through the code. And I think there's really something critical about these moments in the history of computer science where the move towards structured programming, the move towards object-oriented programming, the move towards test-driven development and so forth, where people have kind of stepped back and said, okay, we're sort of bumping up into the maximum complexity of the programs that we can write relative to the amount of complexity that the human mind can fit into its working memory at a time. How can we try to be more disciplined about the way that we're writing code such that it enables us to write ever more complex systems and still feel like we're in some sort of control. So I associate that in large part with Dijkstra also, and I think that's something that has influenced my thinking in terms of by analogy, I think of myself as being kind of like a CPU that's executing this series of instructions, and go to considered harmful is kind of something that I think about in terms of if I'm interrupted by a task, do I then resume the previous task, or do I just sort of end up going off on some tangent? So I try to apply the same discipline to my own time management that one would to thinking about the structure of a program. So that for me is the other sort of interesting dimension of Dijkstra's work that I find myself thinking about again and again.
You explore poker from a variety of angles in Algorithms to Live By. What is useful about poker as a mechanism to look at algorithms through?
I mean, I think game theoretically, there's a couple interesting things about poker, and it, as you say, it comes up in a few different points in the book. And one of the places that it comes up is our chapter on sorting. And the reason we get into poker there's a whole branch of CS theory within sorting on what's called minimum comparison sorting. So how, if you've got 10 items, I mean, the classic way of thinking about it is you have 12 items of unknown weight. They're all the same size. They weigh different amounts. And you have a little scale. And you want to arrange these items from lightest to heaviest. What is the absolute fewest number of times that you can use that scale in order to confidently sort all these objects? And so the passionate listener is encouraged to check out Donald Knuth's tome, The Art of Computer Programming. I think it's volume 3 is entirely dedicated to sorting and searching theory. What we look at in the book is, are there cases where, in effect, nature implements something that's close to a minimum comparison sort? And so the world of what's called heads-up cash games in poker offers us one such case study. And so heads-up poker is just one-on-one, and cash game poker means we're not playing for some abstract, chips that map in a sort of non-one-to-one way to money. We're just playing for actual money. So when I wager $10,000, that's 10,000 actual dollars. So actually, a former classmate of mine in the computer science program at Brown, Isaac Haxton, has gone on to be one of the consensus, top 5 heads-up cash game poker players in the world. And so I spent a bunch of time talking to him about what is that like, what's the thought process like. And he said something really interesting to me that stuck with me, which was, in many ways, the critical skill, the single most important skill of any poker player, is not being good at poker. It is knowing exactly how good at poker you are. If you are the 3rd best player in the world, but you insist on playing the 1st and 2nd best player in the world, you will go bankrupt and you will not have a career. And so that for me was just a completely fascinating insight. And it leads one to wonder why top poker players agree to play each other, because there's actually a very high degree of consensus within the poker community of what the stack rank of the top 20, let's say, people are. And in fact, this is what you see. You often see, the number 1 player issues a challenge to the number 2 guy who declines. He then in turn issues a challenge to the number 3 guy who declines, and so on and so forth. And there's actually this funny stasis that you see at the top levels of the game. And so whenever 2 people agree to play, heads up cash poker, it can only be because they both feel that they are the superior player. And so this, I think, corresponds really nicely to some of this theory that exists in the world of sorting on, what is the absolute fewest number of head-to-head comparisons that are necessary to produce a stable hierarchy. And we also look at this question in primatology. If you look at dominance hierarchies in chimpanzees and macaques and so forth, you find that, and there are people who have done work on this, you find that nature appears to implement something close to an optimal, minimum comparison sort, because in these cases, the comparator operation is simply that the primates literally come to physical blows. And so, it's in the interest of the entire tribe that happens the minimum number of times, and that a stable hierarchy results. And so, I think it's quite interesting to try to bridge the gap between this seemingly arcane theory and the natural world around us, and try to recognize cases where something akin to a sorting algorithm is taking place, whether we recognize it immediately or not.
Yeah, I used to play a lot of poker. I actually played against Isaac Haxton a number of times, and he's that guy is quite a fearsome player. But it's it's interesting because kind of as heads up cash games were really catching on in the online world. There was a lot of 6-player games, and there were some 9-player games around that time when heads up was really catching on. And it was funny because the people who were really dominant at heads up, when they would come and sit down at 6-player games, they would have such an influence on the table. It was like the gravity in the table would shift towards that player, whether it was a real or kind of a manufactured effect, like that dominant hierarchy that you're talking about. It's quite an interesting effect. And I know when I was coming up as a poker player, I remember feeling somewhat ashamed that my approach to the game felt very algorithmic. Like I had just read a bunch of books, and I was reading stuff online, and I was basically copying what other people did. But in reading your book, I was thinking about it as like, poker is just algorithmic. Like you should have an algorithm. If you don't have an algorithm, you should you should probably figure one out. You don't want to be, it's actually not a game of improvisation. There is some elements of improvisation, but in a perfect world, you would have every single point of the decision tree mapped out, because there is a finite number of decisions that you can make in a given hand. It's like you have a state machine that gets generated after every hand, and you should be able to traverse that state machine. But it's interesting. Another interesting thing is that there are certain players who have come up through the ranks. This guy Isildur comes to mind. They come up through the ranks doing things that are totally unconventional, and they're so outside the bounds of what the typical players are doing. Like, they'll do things like overbet the pot, or min raise every open in a heads up game, and sometimes this throws off the experienced players. I don't think this happens as much anymore, because the heads up no limit has been explored so thoroughly. But it is interesting that the algorithms that the top players developed were often a product of the previous algorithms that had come before them, because you're always just developing an algorithm that is simply a counter strategy to the other algorithms that are pre-existent.
Yeah, and you would expect, at least in a purely theoretical sense, you would expect the system to drift towards some Nash equilibrium where there is no longer any room for anyone to, innovate strategically. It's just reached some kind of static point where, everyone's strategy is as optimum as it can get given the ecosystem of other strategies that exists. And this is actually something of an open question within game theory. Is everyone knows these famous theorems that a Nash equilibrium always exists in a zero-sum game, but computer scientists have been able to really push game theory into a new set of questions. And so, for example, in our chapter on game theory, we talked to Christos Papadimitriou, who's one of the people, one of the theoretical computer scientists that's asking a fresh set of questions about Nash equilibria, which is, okay, we have this famous theorem that says they always exist, but as a computer scientist, I don't, in some sense, it's unsatisfying to simply know that it's out there. Tell me how to find it. What is the complexity associated with, what's the computational effort required, let's say, to find where the Nash equilibria are? And the sobering result is that it turns out that in most cases, finding Nash equilibria is effectively intractable. And so it throws this to me is a fascinating development, because it throws the utility of Nash equilibria as a concept kind of out the window, which is to say, if this stable point exists, but none of the players in the game can find it, well, then how useful is that equilibrium as a predictor of the actual behavior of the players in the game?
Not to mention, people tilt all the time, and that throws off the ability to say, like, okay, how close are we as a pair of heads-up players to reaching Nash equilibrium? If somebody's tilting, that kind of throws things off. Yeah,
right. And in some sense, that the existence of genuine tilt is kind of a critical part of what keeps the game interesting, because that makes it possible to bluff that one is tilting, or to that if someone appears to be tilting, you have to ask yourself whether it's for real or not, or what you want to do about it.
When I'm choosing the tools for my side projects, the first thing that I look for is ease of use. That's why I love MongoDB. It is the most popular non-relational database, and it is super easy to use. At the beginning of a project, I often don't know the shape of my objects, and Mongo makes it easy to evolve the database schema as I like over time. Over time, as my project gets popular, I'm going to need to scale, and thankfully, MongoDB has built-in horizontal scalability, but configuration and database maintenance aren't really what I want to spend my time on. Thankfully, MongoDB Atlas was released in 2016. MongoDB Atlas is the easiest way to get access to MongoDB without having to run the database yourself. You pay only for what you use, from small projects all the way up to large production deployments. To try MongoDB Atlas today, go to mongodb.com/sedaily and get a free $25 in credit. Atlas is the only hosted MongoDB service built by the engineers behind the database, the company MongoDB. With Atlas, you get end-to-end encryption, you get VPC peering, you get access to the latest releases, and for a limited time, you can go to mongodb.com/sedaily and get that $25 in credit and get started with MongoDB Atlas. Thanks to MongoDB for being a new sponsor of Software Engineering Daily, and thanks for being the database behind a lot of my favorite side projects in the past. We're really happy to have MongoDB as a new sponsor of Software Engineering Daily.
You write a little bit about the flash crash and the 2008 crisis, and I think of these as interesting examples of herd mentality and the cross-section of herd mentality and gambling. What are the algorithmic lessons and the lessons about human nature that you take away from the market turmoil of, the 2007 through 2009 or whenever that period of time you're looking at is?
Yeah, and then the flash crash was like 2010, I think. Yeah. I think the narrative that always seems to get trotted out in the press after something like this has the character of figuring out who was the bad actor or who's to blame or who made the mistake, whether through malintent or just incompetence. And the story that you get from looking at these sorts of things in game theoretic terms, the framework that I think is the most interesting comes from the early 90s, and it's this idea of informational cascades. And the basic idea of an informational cascade, so I'll give you the kind of the toy example that they use in the literature, which is, let's say you've got two urns, and one has mostly blue balls in it, and one has mostly red balls in it. There's a bunch of people in a line, and each person gets to go up to the urn, which could be one of these two different urns. Someone goes up to it and they pull a ball out at random. They get to observe that ball, but no one else does. And then they have to say whether they think that this was the mostly red urn or the mostly blue urn. And so the critical thing here is that all of the other people get to know that person's guess, but they don't get to know what that person actually saw. And so this is the difference between what's called private information and public information. So let's just say, for the sake of argument, that let's say the urn is 2/3 blue and 1/3 red. Okay, well that means that there's a 1 in 9 chance that the first two people both saw red balls, even though the urn is mostly blue. So there's a 1 in 9 chance of that happening. And if that happens, then the third person goes up to the urn, and let's say they pull out a blue ball, but they say to themselves, well, both of the previous people gave the prediction that it was the red urn. So even though I have private information that goes against that, it's still rational to say that we're dealing with the red urn, even though I've got a blue ball in my hand. And so that person puts that blue ball back, and they say, okay, my prediction is still that it's the red urn. And so the fourth person goes up, and we've now created what's called an informational cascade, which is there's no amount of private information that's going to overcome the amount of public information. So the fourth person goes up, they draw a blue ball, but they still vote red because they have seen 3 previous people vote red. And the 5th person, the 6th person, so on and so forth. And so you can see what happens here, which is there's a 1 in 9 chance of setting off this chain reaction that results in basically infinite misinformation. This is kind of like the emperor has no clothes type of thing, where you say, well, he looks naked to me, but everyone else seems to be saying that he's clothed, so I'm going to discount my private information.
And this is what happened in the flash crash.
Yeah, and I think this offers a sort of a game theoretic framework for bubbles in general, which is, let's say I'm looking at buying an asset, or let's just say a house, right? Let's say I'm thinking about buying a house and it costs $1 million, and personally I don't think it's worth $1 million, but everyone else seems to think it's worth more than $1 million, or so I believe, based on their behavior in the market. So I buy it because I think, well, as long as I can find someone else who believes it's worth that, then it doesn't really matter what I think. But I've made an error here, which is that I've assumed that other people's behavior is indicative of their beliefs, even though my behavior is not indicative of my belief. And so this is a case where, this is how bubbles form, basically. And the sobering story that you get by, looking at the literature here is that, as I said at the beginning, we always want to know who was the bad actor, who made the mistake, who was acting in bad faith or irrationally. And in many cases, the answer can be no one. That I think, this offers a framework for what Tom and I refer to in the book as the tragic rationality of bubbles. There's no bad actor. It may just be a cruel game. It may just be that this is the rules of the game.
And how do you recognize that if you're in the middle of it? Whether you feel like you're in the middle of a bubble of mortgage-backed securities or online advertising, what's the algorithm for getting out of it, or for identifying that you are in a bubble so that perhaps you can make some kind of contrarian bet and take advantage of it?
Yeah, I think the first thing is just recognizing the difference between belief and action. So this is for me just a very key thing, is being reluctant to make inferences about someone's actual beliefs based on what they do. This also comes up in the context of oil drilling rights. You sometimes get these weird bubbles where, all these different oil companies are engaged in a bidding war over a tract of land that actually no one's private survey indicates is rich in oil, but they infer from the bidding behavior of the other parties that the other people do think it's rich with oil. And so they think, well, their studies might be better than ours, so we'll bid on it anyway. And you get a similar cycle that just kind of spirals arbitrarily. So I think the first thing is just recognizing that there is this gap between belief and action. And not being so quick to make that inferential leap, I think, is part of it. The other part of it is recognizing that if you are contrarian, if you're that person that stubbornly doesn't buy the asset because you just don't think it's worth that much, even though you're aware that there's kind of a general consensus that it is, you are conferring a social benefit. There is something in a way altruistic about that kind of behavior. That the person who refuses to go along with the herd will probably, lose money on average, or be wrong more on average than the people that take that information into account. But on the other hand, they may be part of the kind of the mechanism that keeps the system from going totally off the rails.
Yeah, agreed. So, you got 5 minutes or so left. What are the problems or the difficulties in your everyday life that you find are difficult to solve algorithmically? Is there a class of problems that are characteristically not easy to apply an algorithm to?
Yeah, I mean, that's a great question. I usually get the inverse of the question. Is most people who ask me about the book say, "Give me an example of where you apply this stuff to your own life." So I like that your question is, tell me where it fails to apply. So I think one of the thorniest areas in human life is time management. And we have a chapter in the book that's on scheduling theory, and there are two basic problems in scheduling theory. One is that so the typical metric that you would want to optimize if you're doing scheduling is what's called the make span, which just refers to the total amount of time it's going to take you to do all this stuff. And so that's just the most natural metric you'd want to minimize, is like, how do I just finish everything as quickly as possible? There's this little bit of a paradox in the theory, which is specifically in the area of single machine scheduling, where you just have one machine, one worker or whatever that's going to do all the work. And if you're committed to doing all of the work, then it actually doesn't matter what order you do it in, because there's only one person to do it and they have to do it all. So it does not matter what order you do the work in, the make span will be the same. And so this is kind of an interesting anti-result, or a negative result, if you will. And what that means is that the people who are interested in the field of single machine scheduling need to think creatively about other metrics that they would want to optimize for in order to get some kind of optimal strategy to come out, because otherwise you just get this answer that it doesn't matter what you do. And so people have come up with all sorts of different metrics. If you want to minimize the maximum lateness of any given job relative to its due date, then there's this policy called earliest due date, which just says do things in the order that they're due. That's pretty intuitive, but it turns out to be optimal. If you want to minimize what's called the sum of completion times, which is the total amount of time that every task is outstanding, summed over all the tasks, then the optimum algorithm turns out to be this thing that's called SPT, shortest processing time, which just means do the easiest things first and make your way up to the hardest things, which again is intuitive, but it's cool to know that there's an optimality result there. And the point that we make in the book is, there's this idiom that says, a man with one watch knows what time it is. A man with two watches is never sure. And I've always loved that quote, and I think it sort of rears its head here, which is to say, in single machine scheduling, there is not a single optimum approach, but a plethora, depending on how you want to frame the thing that you're trying to do. And so this is something that I think a lot of bestseller self-help books on time management miss, is that if we can't even begin to talk about the right answer to the question of what should I do next until we have gone much farther in articulating exactly what the question is that we're asking. And that's something for me, that's been an interesting takeaway when I just think about my own life, which is I think it's pretty typical that we find ourselves in a situation of saying, what do I do now? What do I do next? How do I plan my day? And in many ways, we're jumping the gun. We are leapfrogging the essential first question, which is, what exactly am I trying to do? Am I trying to get the most stuff crossed off of my list as quickly as possible? Am I trying to make sure that nothing goes too far overdue? What exactly are my aims? And I think personally, I'm probably as guilty as anyone in terms of I don't always take the step of articulating that to myself, and so that it's been a nice reminder to kind of take that first step.
So what are you working on these days?
I am now working on the beginnings of a new project which looks at the intersection of machine learning and ethics. So I think we're at a really interesting moment in the progress both of technology and of policy. We are increasingly turning over more and more aspects of the functioning of society.
Such as the news cycle?
Yeah, actually, that's a perfect example. Yeah, I mean, the one that I had in my mind was there was the investigative report that came out a couple weeks ago looking at the algorithms that predict prisoner recidivism, and assign a kind of a risk to reoffend that is now being used by human judges as a way to figure out which prisoners should get parole and who should be released and so forth. And there was a bunch of systematic, in this case, I think racial bias that was found in this algorithm. And I think we're really at this interesting crossroads where we have a lot of work to do to figure out how to translate the values that we have as a society of equality and fairness and justice and opportunity into algorithmic terms. How do we put what are the exact constraints that we want to put on this statistical system or this machine learning system in order to feel confident that the recommendations that it's spitting out conform to our set of values. I think that's kind of an open research problem, and it's also an open policy problem. And we're sort of hurtling into a world in which we need answers pretty quickly, because this stuff is getting deployed faster than we can figure out, on the theory side, exactly how to make sure it's doing what we want. So that to me is a really, really interesting area, and I think there's a lot to be said about that.
Cool. Well, I look forward to seeing what fruits that work bears. I hope everybody checks out Algorithms to Live By. So thanks for coming on the show.
Yeah, thanks for having me, Jeff. It's been a pleasure.
Software Engineering Daily is having our first ever meetup in San Francisco, January 11th at Galvanize. If you live in the Bay Area and you listen to Software Engineering Daily, please come check it out. I would love to meet you. We're going to have some awesome speakers. We have Pete Hunt, who is one of the early members of the React.js team, who is now the CEO of Smite. Hasib Qureshi, who has been one of the most popular guests on Software Engineering Daily. Preeti Kasireddy, who has written about her career transition from venture capital to software engineering via Coding Bootcamp. Each one of these speakers is going to give an awesome talk, and I hope you can make it January 11th at Galvanize in San Francisco. You can sign up on meetup.com. You can also find the link on the Software Engineering Daily website, softwareengineeringdaily.com. I really hope to see you there.